All right, so we're going to start out at square one with this class, and we're going to talk a little bit about the history of chemistry. Does anybody know the origin of chemistry? Like, historically, how did chemistry show up in our society? Does anybody know? What do you think?
Wasn't the search for alchemy for chemistry science?
Yeah, exactly. So alchemy is actually the beginning of chemistry. Does anybody remember what alchemy is? Yeah. Yeah, alchemy is where you try to change something like lead into gold. And so that was really popular for a long time. People thought it could be done, and they did all sorts of wacky experiments trying to figure it out. And really, that's the origin of chemistry, is trying to figure out how to turn things into gold. Until about 1661, when this book came out. It's called The Skeptical Chemist. And basically, it was a book written by Robert Boyle saying that all of that mystic alchemy stuff isn't legitimate science. And so alchemy eventually evolved into chemistry. And like I said, this was done by Robert Boyle in 1661. So it's relatively recent in terms of our science understanding, and it's evolved as time has gone on. So for example, in 1661, they didn't really have a firm idea of what an atom was. They just kind of understood that matter could be changed in certain ways. The interesting thing, too, is through the 1900s in particular, chemistry branched out into a bunch of subdisciplines. So if we look at this, obviously medicine is a huge subdiscipline of chemistry. We've got neurology, paleontology, geology, physics, electronics, meteorology, metallurgy, engineering, archaeology, ecology, agriculture, botany, biology, biochemistry, pharmacology, and toxicology. One of my favorite quotes I remember from undergrad was my professor said, biology is really chemistry, chemistry is really physics, and physics is really math, right? There isn't really a firm line between any subject anymore. There's a lot of crossover in between fields. And it's one reason I like chemistry is it's kind of smack dab in the middle of all these science fields, right? So we do a lot of math, we do a lot of physics, we do a lot of biology and chemistry. All right. The next thing we got to briefly talk about is something that seems pretty intuitive to us now, but is the foundation for all science, and that's the scientific method. How many of you guys remember this from other classes that you've taken? Yeah? It's a pretty common thing that's talked about, especially in high schools. The first thing you do in the scientific method is you simply make an observation, right? So for example, you could say this tree tends to grow really, really well in swamps. That's an observation, right? So that's the first thing you typically do is just make some sort of observation in the world around you or in nature. And then you end up thinking of a question. It's always the next step is we don't just stop at the observation point and say, hey, that's cool. We actually try to apply a question to it. And then after we come up with a question, we like to develop something called a hypothesis. Does anybody know what a hypothesis is? Yeah.
Educated guess?
Yeah, it's an educated guess. That's a really good way of thinking about it, right? So a hypothesis is basically coming up with some sort of general cause for a phenomenon. And we'll go over some of these definitions in a little bit. But a good way of thinking about it is it's a testable or educated guess. And then what we do is we make a testable prediction. And we say, all right, if this plant grows really well in a swamp, let's maybe make an artificial swamp and see if it grows well. And then maybe we'll make an arid region and see if the tree doesn't grow well there. So we go from our hypothesis to our testable prediction. And then after we develop our testable prediction, we want to go out and test it, right? So we gather data. To test our prediction. Makes sense, right? As a chemist, we always want to do experiments. The reality is, most of the time when we gather data, we learn something new that we hadn't thought of before. So what we do is we get stuck in this feedback cycle where we refine, alter, expand, or reject our original idea. And this feedback loop can go on and on and on for quite a while. Oftentimes, chemists will spend years and years stuck in this kind of feedback loop of constantly testing a prediction. After you do this a certain number of times, though, you can develop a general theory. And a theory is something that's an explanation that's consistent with all of the data that you've collected up to that point. Oftentimes, too, this can further feedback into making a new observation to kind of double check that theory. A theory is only a theory if it's supported by all of the data that you've collected. And so chemists are always in this hunt of trying to disprove or prove things as much as possible. Does that make sense? I know it seems kind of elementary at this point, but it's kind of groundbreaking that they came up with this around the 1600s, and we've been able to turn this into all those branches that I showed you previously. All right, so let's go into some terminology. Terminology is a big deal in science, and oftentimes people misuse the terminology, so I'm going to be kind of a stickler with using the correct terminology. And we'll go back to the hypothesis. Can you guys see this all right on the board? Just want to make sure. Okay. Hypothesis is an educated, testable, and I'll put guess, about an observation. So scientists always like coming up with a hypothesis. Next, we have theory. And like I said, theories are typically towards the end where you've collected a lot of data, and it's some sort of general explanation that's supported by all of your data. And the key word here is an explanation. Oftentimes the word theory gets misused, especially in the media, where people will say, well, that's just a theory. That's not really a good way of refuting something, is it? Because a theory is supported by data, a theory is something that's absolutely true as far as we know at that point in time, right? A theory isn't a theory if we have data refuting it. So theories are the bedrock of all of science. After theories, we've got laws. And laws show up a lot in science too. And laws are different than theories, and I'll show you a simple trick for determining the difference between them. But laws are a summary, not an explanation. It's a summary of a large body of data or info, but provides no explanation. Right, so if you think about Newton's laws, right? Newton said mass times acceleration equals force, right? That doesn't explain how things are working. It's just saying, here's a good summary of all of the observations that we're seeing. So it doesn't have an explanation component. The way I typically remember laws is laws quite often have a mathematical formula associated with them. So often a formula. So Newton's laws are a really good example of that, where all of his laws can be presented as a mathematical formula. Does that make sense so far? Make sure you don't confuse theory and law. That's a common one that people mix up, and they say, well, it's a law. It's like, no, that's a theory. A theory is an explanation. A law is just a summary of a lot of information. All right, so now we got to get into the critical thinking aspect in science. And I know a lot of this, again, will seem kind of elementary, but I like going through this and providing you with some examples of bad science too. And so the textbook that we use, I really like the acronym that they use for critical thinking. They call it FLARES. So F-L lowercase a-R-E-S. And the F in here stands for falsifiability. And basically what this means is that there must be a conceivable way to prove something false. So there must be a conceivable way to prove your claim false. So if you think about something like astrology, where maybe they're looking at a line in your hand and predicting how long you'll live, there's not really a good test you could do to prove that incorrect, right? So scientists like doing tests where there's a theoretical outcome that would disprove your hypothesis, right? The next one is L, and that's logic. And really this is self-explanatory. We must use logical reasoning. So we can't come up with some sort of mystical attribute for why something occurs. We have to have some sort of logic that we can test and prove, or disprove for that matter. Next one is reproducibility. And again, that means that your data must be reproducible. This is one of the hardest things to do in science. In fact, there's a lot of debate going on specifically with psychology, that a lot of the papers coming out in the field of psychology aren't reproducible. And that's not scientifically valid unless you can reproduce it. And it's becoming a problem because more and more scientists have this pressure to publish. There's this phrase called publish or perish, right? So there's a lot of pressure to publish, but if you're publishing stuff that's not reproducible, that can actually backfire on you. You can have a new article published basically refuting all of your findings, and that looks really bad on your record if you just publish a paper that got refuted. All right, and then lastly, we need sufficiency. And that basically means that your evidence must be adequate. Sorry if my penmanship's not super great. So those are the main four components of critical thinking in science. They're really important, though. There's a few other things, though, that I did want to hit on, especially in the area of sufficiency. Yep?
I was going to ask what you mean by adequate.
I'll show you some examples of that, because it is kind of a nebulous term that's not easily explained. So, for example, what I mean by that is the burden of proof always lies on you. And what I mean by this is you can't just throw out a crazy claim and then not provide any sort of evidence to back it up. If you're putting out a crazy claim, it's up to you to come up with evidence to support that claim, right? So that's a really important aspect in science. The other thing, too, is if you notice I put proof in quotation marks. The reality is scientists don't like using the word proof. We can say we came up with extraordinary evidence supporting something, but quite often we can't prove something. Proofs are typically used in mathematics, not in science, right? So in math, you do proofs. In science, you come up with overwhelming evidence. So that's an important thing to remember. And then extraordinary claims require extraordinary evidence. So if you say that I'm capable of flying as a human being, I've got to come up with a lot of good evidence showing that I can fly, right? Not that I can. The other one, too, that's my personal big pet peeve is correlation is not causation. So correlation does not equal causation. And this is another one that's a big problem, especially in the media, is we really like those flashy headlines that show some sort of link. The latest one, right? Have you guys followed the coffee warnings? So the state of California wants to label coffee, saying that coffee has a chemical compound in it that's been potentially associated with cancer, right? That's kind of not saying anything super significant. If you look in California, they actually label sand as being a possible cancer-causing agent. And so it is one of those things where correlation isn't always causation. You have to come up with an extraordinary amount of evidence to actually link two things together. I'll show you another one, too. I like this one too because my wife works with kids that have autism. Oftentimes you'll see in the news these weird things that say, oh, if you look at organic food sales, for example, it tracks really closely to the incidences of autism. Does that mean that organic food causes autism? No, it just means that you found two things that are somewhat related to one another in terms of their trend lines. It doesn't mean that they're a cause and effect relationship. So I really like this as an example. How many of you have seen things by the Food Babe online? On Facebook a lot. She has all sorts of crazy stuff on her website talking about like genetically modified foods being linked to cancer and things like that. Again, there's no causation or correlation going on there. It's just she's throwing stuff out there, and quite often it's just to get ad money. So I always tell people, be skeptical of anything you read in the news and look for the evidence. Try to dig into the sources that you see and see if it makes sense. Don't just trust people at their word. And that kind of gets to my next point. Authority is not evidence. One of my favorite examples of this is with DNA, right? So how many of you know a little bit about DNA? DNA is a double helix, right? So a lot of you remember that from school or maybe from reading online. So that was a pretty big discovery when it came out, and there was a chemist at the time who actually had 2 Nobel Prizes, and he said, nope, you guys are wrong. It's actually a triple helix. And everybody was like, well, he has 2 Nobel Prizes, right? He's probably not wrong. He was wrong. So just because you have 2 Nobel Prizes doesn't mean your evidence is any more valid than anybody else's. So don't just trust people based on their position, title, or authority. You always have to look at the evidence itself before making a claim. Does that make sense? All right. So we are going to jump quickly into physical properties before tomorrow's lab, because tomorrow's lab is all about physical properties. And physical properties are really important in science. They're things that can be measured or observed. And when you measure or observe them, you aren't changing them into a new type of matter. So for example, a good physical property might be something like length, right? Or height. So for example, if I measure a board using a measuring kit, I'm not changing it from one type of matter into another type of matter. It's still a piece of wood. All right, what's another thing we can measure without changing one type of matter into a new type of matter? So if you go to the doctor's office to get your height, and then what's the second thing? Weight or mass. We like using mass. As scientists, does anybody know why we like using mass over weight? What do you think?
Weight change gravity.
Yeah, exactly. So for example, if I go up into the International Space Station, I appear to be weightless, right? I still have mass. If I go back down to Earth, I still weigh something. So quite often we use mass and weight interchangeably on Earth, but the reality is if you're out in space, your weight might be very, very different if you're on Jupiter or Mars or some other planet. All right, next thing we have is volume. What is volume? What do you guys think?
How much area something takes up.
Yeah, how much area something takes up. So for example, a balloon has a specific volume. It's the area inside that balloon. It's a three-dimensional area. All right, the next one we have is density. And how do we define density? Does anybody know that one? So if you're really, really dense, what does that mean? What do you think?
Like a lot of matter in a really small volume.
Yeah, a lot of mass in a really small volume, right? So if you've ever picked up like a shot put or a lead weight in a gym, those are really, really dense, right? They have a large mass in a relatively small volume. Versus something like a balloon, takes up a lot of space but has very little mass, right? So that's not dense at all. In fact, most balloons float if they're full of something like helium. All right, the next one we have is temperature. And temperature is really important for chemists. Does anybody know the units that we normally use in chemistry? Celsius, right? We're kind of goofy in the US. We use Fahrenheit a lot. The rest of the world does not. If any of you have traveled outside of the US, it's kind of jarring when you first see it because you'll see, oh, it's 30 degrees out, but it is really hot. Oh, wait, it's in Celsius. So the rest of the world uses Celsius. Chemists oftentimes use Kelvin as well. I think the only countries that still use Fahrenheit are the US and like Myanmar. There aren't that many countries that stuck with Fahrenheit. The rest of the world all uses Celsius. All right, the other thing we can do is we can measure things in terms of their color. We'll talk more about that later, but you can measure the wavelength of light, right? That's also related to color. You can measure taste. In fact, if you ever go, I'm not sure how many of you are over 21, but if you ever go wine tasting, quite often they'll have like a wheel of different tastes talking about, oh, this wine has vanilla notes to it, or this one has more citrusy notes. You can actually measure a lot of those using chemical processes. So taste is a big one. Boiling point is another big one. So basically, how hot does something have to be before it boils? Does anybody know what that temperature is for water in Celsius? 100. That's why Celsius is so much easier than Fahrenheit, is the boiling point is 100 degrees Celsius. What's the freezing point? Zero. It makes so much more sense to use Celsius. We're just stubborn Americans, so we stick with our system. So we can also measure freezing point. The other thing we can measure is hardness. Seems like kind of a weird thing to measure, but does anybody know the hardest substance on our planet, at least that we know of? Diamond, right? So there's actually a scale where you can measure things based on how hard they are, and at the far extreme, you've got diamonds. In fact, diamonds, the only way to polish or cut a diamond is with other diamonds, right? If you try to actually polish it using normal sandpaper, nothing will happen to it. That's one reason why diamonds are considered so special. The kind of weird thing is diamonds aren't actually that rare. Are any of you guys familiar with that? So it's kind of this weird marketing thing, but I know diamonds are really popular in jewelry. That's kind of artificially created to monetize diamonds. They're not as rare as you might think, but they are still special because they're the hardest substance on our planet. And then last but not least, we can measure things like odor. So there are special techniques that chemists can use where they can actually detect odors coming off of, let's say, a wine or a beer or a type of food, or even in the environment, right? So radon's an important gas that people try to measure, and some gases have very unique odors that can be picked up. Does that make sense so far? All right. We'll go into one more thing, and then I think we'll call it quits. So going back to the mass versus weight thing, I just wanted to drive this home, is that mass is an intrinsic property. That means it's not changed by anything else around it, right? If you've got a specific mass on Earth, you'll have that same mass in outer space or on Mars for that matter. It's an intrinsic property. Weight, on the other hand depends on gravity. So for example, if you're on Mars, you're going to weigh, I think, something like a third what you do on planet Earth. And that actually is a big problem with spaceflight, because you can imagine you don't want to go to a planet where the gravity is so strong that you're crushed by your own body weight. And you also don't want to be on a planet where the gravity is so minimal that when you jump, you actually launch yourself into orbit. So you do have to be careful with that. So how do we measure mass? And what we're going to do tomorrow is start measuring the mass of pennies. Does anybody know what units are typically used for measuring mass? So I'll start out with what we normally use. Whoops. In the US, we normally use pounds. Right, so if you go to the doctor, quite often they'll tell you your weight or mass in pounds. The rest of the world uses kilograms or grams, right? So if you're in Europe, for example, they normally use kilograms. And the symbol for grams is lowercase g, or kilograms is in kg with a lowercase k, not a capital K. So as scientists, we really prefer to use these two. We don't like using pounds at all. In fact, there was a famous example a few years ago where a Mars probe was sent off, and they were all excited for it to land on Mars, and the probe ended up just cratering into Mars. It was going something like 300 miles an hour when it hit the surface. And that was a big mess up. And NASA went back and they tried to figure out what went wrong. What they found out was that the engineers in the US were using American units. And then the physicists and engineers that worked on other sides of the project were all using things like kilograms or grams. That's a huge issue if you're not all speaking the same language. So we try to use these scientific units as grams or kilograms. A good metric too is a cube of sugar is about 4 grams. So I really like estimating mass. So if you can always think about some sort of standard thing around your house, you can use that to roughly estimate. If you notice too, with kilograms, we used a prefix, the K for kilo. We'll talk more about that later, but quite often scientists will use those prefixes when they're dealing with really big numbers or really small numbers. It's easier just to condense them down into a simple unit like kilograms. All right, I think that's where we'll end off today. Like I said, make sure you come tomorrow with your notebook and try to dress appropriately too. I won't kick you out of lab tomorrow because we're just working with pennies, but in the future there might be situations where we have hazardous chemicals out and you do need to wear full coverage pants and shoes.